Okay, I'm going to get started. Today we're going to be talking about a little bit more stuff that's motivated by social choice. We're going to introduce the very important concept of noise stability and noise for Boolean functions. And at the end, we'll prove Arrow's theorem. But I actually want to go over a little bit more influences and total influences and say a few words that I didn't get a chance to say at the end of last lecture. So let me remind you a little bit about influences. And I want to describe how you can think of them also in terms of the geometry of the hypercube. So there's the hypercube in 3 dimensions. And one way you can interpret a Boolean function, besides just as a voting rule, is as the indicator of a subset of the vertices of the cube. Okay, so it doesn't really matter which you choose to be 1 and which you choose to be -1, which are green and purple. But you can think of it as an indicator of a subset of the cube. And if you recall, we define the influence of the ith coordinate on f this way. It's the probability, if you take a random vertex and look at f's value and flip the ith coordinate, the probability that will change the value of the function. Now, if you think about it, picking a random vertex and then flipping the ith coordinate and looking at s values on the 2 points that you get is the same as just choosing a random edge in the ith direction. So what I'm saying here is that this is also equal to, in the case of Boolean valued functions, the fraction of I-directed edges that are bichromatic. Or if you think of f as the indicator of a subset, it's the fraction of I-directed edges that are on the boundary of the subset. They have one vertex endpoint in and one endpoint out. Okay, and with this interpretation, it gives a nicer interpretation, or it's reasonable to look at this thing that we introduced, the total influence, which was the sum of the influences. Now you can see one good reason to sum them is that if I actually just divide both sides here by n, I can think of this as the average, or rather the average of the influences. And therefore, that's in fact just the fraction of all edges that are bichromatic. Okay, because if I average this quantity over I, there's an equal number of edges in each of the n directions. Okay, so up to the scaling factor of n, this total influence of f, if you think of it as indicating a subset, measures the fraction of edges that are on the boundary between what's inside f and what's outside f. Okay, so in that sense, it's measuring some kind of surface area of f as well. Okay. Now, along that lines, we can ask some isoparametric type questions, and we'll answer one such question shortly using Fourier analysis. So let's do something that we also didn't get a chance to do last time, which is give a Fourier formula for the total influence. So if you recall from last time, this is very easy. If you recall from last time, we had this formula. The influence of the ith coordinate on f is the Fourier weight on sets S that contain I. Okay, this holds even for functions into the reals. Okay, so we can get a Fourier formula for the total influence just by adding this up. So the total influence of f is going to be the sum over all I, going from 1 to n, the sum over S containing I, f hat S squared. And as always, if you see 2 sums or a sum and an expectation, you should interchange them. This one's slightly tricky, so we want to sum over all subsets S. And now we have to ask ourselves, how many times in this sum does a particular f hat S get counted? Yeah, it gets counted once for every one of its elements. Every time it has an I, it gets counted, so it gets counted cardinality of S times. Okay, so this is the formula for total influence. And you see, again, it's actually just a function of the Fourier weights. In some sense, it measures like the average degree of the function rather than the total degree. Because remember, the monomials associated to cardinality S have degree, sorry, associated to S have degree cardinality of S. Okay, any questions about that? So now that we have this formula, we can prove a very basic but important theorem. If you remember another formula, this was probably from class 1, the variance of F was also a sum of Fourier weights. In particular, it was just the sum of F hat S squared over all non-empty S, which I can write as cardinality of S is at least 1. Now, if you look at these two formulas, you can compare them term by term. And you see that this one is always bigger because you're always multiplying F hat S squared against, in this case, some number which is at least 1. Both of them drop out the F hat 0 squared term, F hat empty squared term. And so we can conclude a theorem which also has a somewhat grand name named after a French person, Poincare inequality. It's a very simple fact. For all Boolean functions, even to the reals, the variance is at most the total influence. Okay, and we can give this a nice interpretation in the specific case of a function that's Boolean valued, our most favorite kind of function. On the right-hand side, we have something that's like, up to a factor of 1 over n. It's like the fraction of edges that are boundary edges for the subset of the cube which F is indicating. And left-hand side, as we saw earlier, and it's also several times on your homework, if, let's say, alpha is the fraction of points where F is 1, okay, so if we think of the points that have value 1 as being the set that F is indicating, so alpha is kind of like the fractional volume of this set. We know that the variance of F is 4 times alpha 1 minus alpha. Okay, so in particular, this gives a kind of isoparametric inequality. It says if you look at subsets of the cube of a fixed fractional volume alpha, then you have a lower bound on the fraction of edges in the cube that are on its boundary. It's at least 4 alpha 1 minus alpha. And when is this tight? When is the Poincare inequality tight? Yeah. Exactly, yeah. So Poincare is equality if and only if, well, it would have to be that all of the Fourier mass is on sets of cardinality 1, which means that F is linear. Okay. In particular, for F mapping into minus 1, 1, this means that F has degree 1, or equivalently, the weight of F at degree 1 is 1. And we know from the homework that this is equivalent to F being plus or minus a dictator. Pardon me? Oh, yeah. You're right. So this is fine. Maybe I should say degree less than or equal to 1. This should say less than or equal to 1. You're right, or a constant. Thank you. Okay, it's more interesting in the case where alpha is, not 0 or 1. But in particular, for example, if you fix alpha to be a half, this says that the total influence is at least 1. That's like saying the fraction of edges of the cube that are on the boundary is 1 over n. And indeed, that is sharp if F is a dictator. It's half of the cube in one of the coordinate directions. Okay, so this is how you can interpret this as a kind of isoparametric inequality. Unfortunately, this is actually not sharp unless alpha is 0, half, or 1. But it's still pretty good sometimes. OK, so that's all I wanted to say about total influence. And now I'll move on to the main topic for today, which is a concept called noise stability, which can be nicely motivated, again, by thinking about elections. So let's go back to what we were talking about last time, where we had a Boolean function f, and we thought of it as the rule by which an n-voter, two-candidate election is decided. Well, now imagine the following scenario. So everybody goes to the voting booth, and they vote. Let's say we vote. So x1, it's not a great marker. Say x1 through xn are the true votes. OK, but let's imagine that, I don't know, when you hit the button on the voting machine, that maybe there's some chance that it misrecords your vote. OK, so maybe there's some misrecording or some error in counting the ballots. And we can imagine that these votes somehow get corrupted into the recorded votes. So f of x is what the outcome of the election should be according to the true votes or will to the voter, and somehow f of y is what the reported outcome of the election would be based on the misrecorded votes. And we're naturally interested in the question, what happened? Is it true that the reported outcome is what it should be? In particular, we may be interested in the probability of this occurring, let's say under this impartial culture assumption that we used last time, which was that the voters voted uniformly and independently. Now, we still can't answer this question exactly yet because I didn't say what model we're imagining for the misrecording of the votes. But let's take the most simple model that you could imagine, which is such that every vote independently gets corrupted with some probability, hopefully a small probability. OK, so we'll make the simplest possible model for these misrecorded votes. And I'll give a definition for it. So fix a string x in -1, 1 to the n, and also a parameter rho, a real parameter in the range 0, 1. And we're going to define this distribution on strings y. We'll write y is drawn from this distribution n sub rho of x. You can think of this x as standing for noise. And we say that y is rho correlated to x. It just means that for each coordinate I, yi is set to be xi with probability rho, and plus or minus 1 uniformly with probability 1 minus rho. OK, and this is independently for each I. OK, so you just go through all the votes. There's some parameter rho. Think for this, most of this class as rho being close to 1. OK, so for each vote, you hold it steady with probability rho, and otherwise you re-randomize it. OK. It's also helpful to do a simple calculation. What's the probability that yi equals xi? Well, with probability rho, they're definitely equal. And with probability 1 minus rho, they have a half chance of being equal. OK, so this is half plus a half rho. Naturally, the probability that yi differs from xi is half minus a half rho. And actually, now that we have this, we may as well allow rho to be negative. or at least between -1 and 0. Okay, this definition doesn't make sense for negative rows, but this one does, so we'll just generalize to this case. So this row kind of measures the correlation between xi and yi for each I. In particular, just so we're clear, if rho equals 1, what does that mean about the random string y? Right, it's always equal to x. Similarly, if rho is -1, y is always equal to -x. And what if rho equals 0? Pardon me? Yeah, but stronger than that, they're independent. So y, well, in particular, y is independent of x, and it's uniformly random. Well, x is not a random variable, so I just mean, in the colloquial sense, independent of what x is. Okay, but these are like the sort of extreme cases. As I said, mostly try to think of the case where rho is close to 1, which means that for each coordinate, most of the time it equals xi, but occasionally it's the opposite of xi. Okay, so this is, remember, this is like x is totally fixed here, and then y is a random string. It's also quite natural, especially if we're going to analyze this picture, to imagine the case that x itself is uniformly random. And in fact, we'll say that a pair of strings, x, y, is a row correlated random pair if it's generated like this. So I mean, x is uniformly random, and then y is drawn from this row noisy distribution. Now, actually, the way I've written it here, it looks asymmetric. Like, first you draw x, and then y is a noisy copy of x. But if you think about it for a few seconds, you'll see that actually this definition is symmetric in y and x. Because, in particular, with this definition, certainly, the probability that xi equals 1 is a half. That's by definition. But that's also the probability that yi equals a half. Because, well, xi is uniform, so yi will also be uniform. Yeah, thanks. That would be weird. Okay, and so these are just random bits. So that actually fixes the sense that it's symmetric. We can also calculate xi, yi, expected value of that. So to calculate this, you can see that with probability rho, these are equal by definition, in which case you'll get 1. And then with probability 1 minus rho, they're like uncorrelated, so the conditional expectation is 0. So you just get rho times 1, which is rho. Okay. So really, this definition, x and y are a row-correlated pair, is the same as saying you just draw the strings x and y sort of jointly. Each of the pairs of bits, you choose this pair from some distribution, this one from the same distribution independently, and so forth. Okay, so each pair of bits has this property. They're 50-50, but they have correlation rho. Okay. Any questions? So now that we have enough definitions, we can make a definition for this quantity. And we can study this quantity. So we kind of want to know, given a Boolean function, if we take a row correlated pair, that's like the true votes and the misrecorded votes, what's the probability that the outcome of the election stays the same? Well, it's a little more natural to look at, let's say, this quantity, the expected value of f of x, f of y, where x and y are a row correlated pair. In general, if f's range is plus or minus 1, then this is more or less computing what we want. It's 1 if the outcome has not changed, and it's minus 1 if the outcome has changed. But this is a nice definition in the case of general functions whose ranges are. So this will be our definition. Let's say row between minus 1 and 1. This is called the noise stability of f at row. And it has this notation. Okay, so it sort of measures the correlation of f with itself when you feed it in row correlated pairs. And just to say what I was saying earlier, if f's range is minus 1, 1, then this is 1 when they're equal, minus 1 when they're unequal. So it's probability that f of x equals f of y minus the probability that they differ. This is 1 minus the probability they differ, so it's 1 minus twice the probability that they differ. Okay, so for Boolean valued functions, this noise stability is going to be some number between minus 1 and 1. And you see it's close to 1 if and only if the election rule is kind of stable under noise. It's unlikely to have its outcome changed due to these flipped votes. Okay. This is a nice quantity that we'll be studying for a fair portion of this class. I hesitate to do this, but let me add one more definition. Just because in the case that I want you to think about most, row is really close to 1. You know, there's only a small chance of flipping the votes. And usually, therefore, the stability is close to 1. You hope that it doesn't change the outcome too much. So it's kind of annoying if you have two numbers, both of which are like 1 minus something small. So effectively, we make it a trivial definition that gets rid of those 1 minuses. And this is called noise sensitivity. And I'll only define it for functions that are Boolean valued. So given f and some parameter delta between 0 and 1, but think of delta as very small, we define the noise sensitivity of f at parameter delta to be the probability that f of x differs from f of y when x is uniformly random and y is formed by flip each bit of x, negate maybe I should say, with probability delta independently for each bit. Okay, so it's really like the same experiment and essentially the same thing, but it's just quantifying if everybody votes at random, then I flip, not re-randomize, but actually negate each bit with probability delta. What's the chance that that flips the outcome? Yeah?
So this is I don't know if this is a well-defined question, but I don't understand the motivation for that definition when we're going into the real numbers. Like anytime we're going into 1, -1, it makes sense, but if f is like 0 half the time, then that's going to be really low just because of that.
That's true. It's a little hard. I mean, this doesn't have like a tremendously great interpretation for generally real valued functions. So mostly we care about the case where f's range is plus or minus 1 or maybe also 0. where it has some combinatorial meaning.
I guess it's also about the norm. If f is 0 most of the time, its norm would be low. So I guess we are comparing stability with the norm of the function.
Kind of. It's kind of like a modified inner product. I mean, remember we have this inner product we love between functions f and even g, which is expected value over random x of f of x, g of x. And yeah, it's true, this has more of a combinatorial meaning if f and g have range, let's say plus or minus 1. But I don't know, somehow this is also at least a sensible definition for real valued functions. And this is also an inner product, actually, for positive rho. It's just a slightly different distribution on the inputs. So part of the answer is just, we define this for real valued functions because we can, and it's somewhat elegant. But mostly we care about it for the functions we care about that are Boolean valued. OK. So I wrote this experiment out in words, but can somebody tell me this is just the same as saying that x and y are a, what should I fill in the blank here, a correlated pair? Yeah, somebody got it real quick. It's 1 minus 2 delta. I guess you can tell fairly easily from this formula. OK, so in light of that, I mean, and just also using what's on the board there, this noise sensitivity is like a half minus a half the stability at 1 minus 2 delta of f. So it's really not like a new concept in the sense that it's like the same as the stability up to like doing a lot of half minuses and 1 minus 2, this or that. But sometimes it's more convenient to talk about this quantity. Yeah?
Silly question, but the requirements of row correlation seem to require that each bit is determined with 1/2, and that doesn't seem to be a requirement for noise sensitivity, so I'm not sure exactly.
Oh, yeah, sorry. This means uniformly.
So uniformly is, in fact, part of the definition of, okay.
Yep, yeah, yeah.
I see.
Mm-hmm. OK. Any more questions? OK, good. So let us do a couple of examples just to make sure we got it. I'll erase this one, I guess. OK, so what's the noise stability at rho of the constantly 1 function? This is easy. I guess it's too easy. It's 1. Yeah. Which is sort of, all these examples will be for Boolean valued functions. So notice in this case that the stability will be between minus 1 and 1. So this is kind of maximized. I mean, the function can never change no matter what you do. Same as if this were minus 1, of course. How about the stability at rho of a dictator function, chi I? Some awesome whistling going on out there. Yeah. Stability, forget about delta. Well, is it too easy? Are you too distracted by the whistling? I know I am. OK, well, I'll tell you, it's rho. It's just rho. Because I erased it here cleverly. Remember, the third sort of equivalent way to state this is that the expected value of xi, yi is rho. And that's exactly what we're computing. So I'll do it more generally, and it could be clearer. The noise stability at rho of a parity, a general parity function, let's say on the s coordinates. Well, let's just compute it. This is the expectation over x, y, a rho correlated pair of chi s of x is just the product of xi for I and s, which we wrote like that, times the product over I and S of y sub I. Okay, so this is the expectation, the product over I and S of xi, yi. And in this experiment, the coordinates are independent, so we can exchange the expectation and the product, like so. Okay, and each of these quantities is rho by definition, so this is rho to the cardinality of S. For example, in particular, I'll squeeze it over here. You see this is going to 0 very fast as S gets bigger. In particular, the noise sensitivity at delta of a parity, it's just going to be a half minus a half 1 minus 2 delta to the cardinality of S. Okay, I just used this formula here. So if you just want to imagine what this means, imagine your election rule is you take the parity of all the votes in the voter set S. Okay? And then there's a little noise introduced into the recording of the votes. Everybody votes at random. There's an outcome. And then each vote gets flipped with probability delta. And you ask, what's the chance that that flips the outcome of the election? Well, as you might not be surprised to learn, if you're using the parity rule, a little bit of noise kind of essentially screws everything up. And as soon as S gets big, this gets driven down to 0, and so the outcome changes with probability close to a half. Okay? Let me do one more example. This is like the most important example for democracy. What is the noise stability of the majority function? So what's the probability that errors in the votes affect the outcome of an election based on majority? Well, it's some quantity, much like this one, that depends on rho and on n. And there's no nice formula for it, sadly. But there is, happily, like an extremely nice formula if you look at the limit as n goes to infinity. Okay, so if you fix rho, then let n go to infinity through the odd numbers, this tends to a number that depends only on rho. And it's 2 over pi arcsine rho. Okay, that's kind of crazy looking, but we'll prove it in about a month. We could prove it today, but we'll just do it later. We prove this using the central limit theorem and some geometric considerations. Well, let me plot this for you. Well, up to the 2 over pi, you see this is the rho axis. It's just the inverse function of sine, the trigonometric function sine. So you should just take the plot of sine and reflect it in the diagonal. So it looks like this. I don't know if that's a great drawing, but like if you tilt your head this way, it should be like a sine curve, also reflected. Okay, so you see, I mean, this is nice, assuming the number of voters is large, that the closer rho gets to 1, meaning the less noise there is in the recording of the votes, the closer it is to the case that the outcome of the election does not change. And in particular, this is one reason why it's sometimes nicer to look at noise sensitivity. What's the noise sensitivity at delta of majority? Well, again, let's take the limit as n goes to infinity. Well, it's like half minus a half something on this. But in particular, if you think about delta as small, like if this is 1 minus delta, you go up here. If you think about it, like if you have like a sine wave, and you're asking if I do a little change here, how much does it change here? It's quadratic if you look at the Taylor series. I'm not going to really belabor the point, but the point is that if you go delta this way, this change is like root delta. Okay, so this goes to something that's proportional to root delta. There's even a constant of proportionality, which is not important. It happens to be 2 over pi. OK, but this is just the same as this, and then I took a Taylor expansion, which is interesting. It says, if each bit in a majority election is flipped with probability delta, the outcome changes probability something like square root delta, which is much bigger. So if this is, like 1%, this is like 10%. 2 over pi times 10%.
Does that mean we should vote?
Well, I mean, we already discussed the fact that, like, in a majority election, everybody has negligible influence. So, yeah, I guess it also depends on. Yeah, there's a whole long social choice and philosophical debate about why people are do or don't vote. Somehow the whole influence thing is clearly wrong, because if you see, like, people go to elections, they can vote for, say, the president, but usually there's also like some other like elections, like who will be the school board trustee or whatever, and a lot of people leave those blank, even though they're right there. It's like utility costs extra 0 for them to vote, and because in these elections there are many fewer voters since they're local, they have way more influence. So there's like no extra utility, they have way more influence, but still they leave it blank. So it's hard to predict what voters will do.
I'm assuming that people vote randomly. I also assume I vote randomly, so why would I vote?
Yeah, that's true. Well, I can always, in the end, just fall back on, well, forget all the voting stuff. This is just Boolean analysis. Yeah?
So this kind of analysis that we're doing is like if we, if each vote is misrecorded with a certain probability, then what's the probability that the vote changes?
Yep.
If you change that a little bit to say like, okay, I know now that a specific number of votes were misrecorded, but I don't know which ones.
Yeah.
Is that harder to analyze the probability that changing 100 out of the votes?
Yeah, that's a great question. The question is like, here basically we imagine, let's say, flipped each vote with probability delta. It means you're basically going to flip around delta times n votes, but it's going to waver a little bit. What if you just like fix the number of votes to flip, like 1,000? At a high level, they're similar. It's much more painful to do like Fourier analysis or analyze that, because you don't have independence across the coordinates. And in particular, some things can get a little screwed up. For example, if it's like the parity of all the bits, you know that if you flip exactly 1,000 votes, it'll never change the outcome. And if you flip exactly 1,001 votes, it'll always change the outcome. So you run into these annoying like parity issues. But that's kind of the only real annoying issue you run into. For example, if half the time you flip 1,000 votes and half the time you flip 1,001, that is quite similar to doing delta noise with delta equal to 1,000 over n. OK. Great. All right, so that's noise stability. Now, I would like to work towards a Fourier formula for noise stability. So to that end, I'll introduce another operator. I should add that, like, hopefully this is going to be the last class that includes a lot of definitions. But we got to get through this. So this you may call the noise operator with parameter rho between -1 and 1. And for some not especially explicable reason, it's denoted T sub rho. T does not really stand for anything, so you just have to get used to it. It's an operator on Boolean functions. With the following action. T rho of f is also a Boolean function with range r. And its value at a string x is just the expected value of f of y when y is like a rho noisy version of x. Okay? So the best way to think of this operator is like a smoothing operator or some sort of convolutional operator. You know, given f, t row of f at a point is, instead of just f's value at a point, you kind of average f's values over a neighborhood of x at a high level. You should, again, especially if you think of rho as being close to 1, you know, mostly you're picking up strings y that are close in Hamming distance to x. Okay, so this is an operator that kind of smooths out functions f. Okay, and let's see how this is very closely connected to noise stability, as we'll show in a second. But let me start out by understanding how it operates on the Fourier expansion. So if I know the Fourier expansion of f, what is this Fourier expansion of t row f? Now the answer is that t row f of x has this Fourier expansion, sum over s and f hat s x s. So far it looks exactly the same, but then there's a factor, rho to the cardinality of s. Okay? So you take the multilinear expansion of f, you take its Fourier expansion, and for each monomial of degree k, you just multiply the coefficient by rho to the k. Okay? So it sort of attenuates all the high degree Fourier coefficients exponentially. And you can even see that it sort of acts as like a smoothing operator in some sense on the Fourier side as well. It kind of, I don't know, smooths out the high degree Fourier coefficients. Okay, so that will be an important formula. And let me do the proof of this. Well, it'll be very similar to the proof we used to compute the Fourier expansion of the derivative operator applied to a function. So the first thing I'll observe is that t row is a linear operator. Okay, in the sense that t row applied to f plus g is equal to t row of f plus t row of g. Okay, and that just follows immediately from the formula for t row and linearity of expansion. If you just plug in f plus g, you can separate out the f part and the g part. Okay, so as we saw in that earlier proof with the derivative, since it's a linear operator, it suffices to check this formula on each of the monomials. So therefore, it suffices to check a t row of x, let me write it down here. T row of the function, the s parity function, is indeed equal to rho to the cardinality of s times this monomial. And that's very similar to this. Just by definition, this is the expected value over y, rho correlated to x, of, well, product over I in s of yi. This is y superscript s. Okay, and once x is fixed and y is drawn in this way, y's coordinates are independent. So this is product over I and s, expected value of yi. Okay, and when x is fixed, what is the expected value of yi? Well, we know with probability rho, yi is set to xi. And with probability 1 minus rho, yi is a random bit, which has expectation 0. Okay, so this is just rho times xi. And so this is, you'll get cardinality of s copies of rho, and then you'll get product over I and s, xi, which is this. Yeah?
So how does this tie in with Parseval's theorem? I would say like the sum of f hat s squared should be 1.
Right.
But then TP of, or T row f has, basically it's like T row f hat s should be rho to the s.
Times f hat s.
Smaller.
Yeah, the question is about how this jives with Parseval. It's a good question. And the answer is that if f is a function let's say into the set minus 1, 1, then t row of f will not, in general, be a function into, it will not have Boolean values. In particular, you see it's the average of a bunch of values of f. So it's the average of some numbers that are plus or minus 1. So it won't likely be plus or minus 1 itself. About the best you can say is that it'll be a number in the real interval from minus 1 to 1, because it's the average of a bunch of numbers that are plus or minus 1. So Parseval says that the sum of the squares of the Fourier coefficients is equal to the expected square of the function, which is consistent. This guy's expected square will be less than 1 because it's got range in the interval minus 1, 1. OK. Good. So there's an obvious, I introduced this t-row operator because of its connection to noise stability. And now we can just check, of course, that what the connection is. The stability, noise stability at rho of f, is the expected value over x, y, rho correlated, f of x, f of y. And let me just break up this experiment of choosing x and y into two parts. So first I'll pick x uniformly at random. Okay. At that point I know f of x, so I'll stick it here. And then the second part is to choose y, rho correlated to x. Okay, and what's left over inside this expectation is f of y. Okay. But you see this piece here in the inside is just t rho f at x. By definition, so we have the expectation over a random x of f of x times t rho f of x. Or this is the correlation between two functions. We may write it as the inner product of f with t rho of f. So whenever you have the correlation of two functions, or their inner product, I should say, you can use Plancherel's formula on that. So as a corollary, well, let me just continue the calculation. F t rho f, Plancherel tells us that this is the sum of the product of the Fourier coefficients, f hat s, and then t rho f hat s. Okay, and we know what that coefficient is. The coefficient on x to the s here is rho to the s, f hat s. So we get rho to the cardinality of s times f hat s squared. Okay, this is the noise stability at rho of f. Okay, so we have sort of yet another nice formula that interprets a combinatorial quantity. If f is Boolean value, this probability that the outcome of the election will change due to some misrecorded votes to the Fourier expansion, in particular the Fourier weights. In fact, if you recall this notation I'll use today, I wrote W superscript k for the sum of the weights at degree k, or at cardinality k. This can also be written as just the sum, k goes from 0 to n, rho to the k times this weight. Okay, so for Boolean valued functions, we know that the sum of all the weights there is 1. As you see, when you look at the noise stability, this kind of attenuates the high degree weights. And it will give you a number between minus 1 and 1. Between 0 and 1 if rho happens to be non-negative, which is the usual case. Any questions?
So we can extend everything to real functions?
Yeah, this is actually all fine for real valued functions. This formula is even for f into r.
In that case, the definition of stability is the left hand, is the left one.
It's this definition right here. Let me do one quick calculation, and then we'll move on to Arrow's theorem. I started this lecture by asking this little problem among, let's say, unbiased functions or functions that were indicators of half of the hypercube, which has the least total influence? And the answer was dictators. We can also ask the same question about minimizing noise sensitivity, which is also a similar measure in a way to the total influence in the sense that it measures the boundary of a set that f is indicating. Instead of picking a random edge of the hypercube and asking, is it crossing the boundary between f's 1s and f's minus 1s, you pick sort of like a random longer edge, one where the fraction of coordinates on which the endpoints differ is something like delta n. So you could ask about minimizing that noise sensitivity or about maximizing the noise stability of a Boolean function for, let's say, unbiased f. I guess that's not a full sentence, but you get what I mean. And in fact, let me also throw in rho non-negative. And in fact, you get the same answer, that the maximizers of this are the dictator functions. And the proof of that is that this thing, we know, its sum, k goes from 0 to n of rho to the k times the Fourier weight at degree k. It's this formula. Now, since it's unbiased, I can write 1 here, because the Fourier weight at level 0 is 0. Remember, a function is unbiased if the empty Fourier coefficient is 0. OK, so this is, let me write it. It's rho times the weight at level 1 plus rho squared times the weight at level 2 plus rho cubed times the weight at level 3, etc. And this is at most, I mean, rho squared is smaller than rho, and rho cubed is smaller still. So this is at most rho times the weight at level 1 plus the weight at level 2 plus up to the weight at level n. And this whole quantity, the sum of all the weights except for the empty one, but that's 0 anyways, is 1 by Parseval. So we can conclude that the unbiased function, which maximizes the noise stability, well, we can conclude that this noise stability is at most rho. But furthermore, we again have equality here if all of these guys were 0 and all the weight was at level 1. Okay, which we know, again, is equivalent to f being a plus or minus a dictator. OK, I went over that a little bit fast, but let me go on so we can prove Arrow's theorem. OK, so to talk about Arrow's theorem, we should cast our mind back once again to France in the 18th century. The French Revolution was going on, and there's all these Enlightenment philosophers and so forth. One of whom was this guy called Condorcet. He had a tragic ending. He died under mysterious circumstances in jail in the French Revolution. But just before that, he was thinking about probability and voting. And he actually wrote a tract called Essay on the Application of Analysis to Probability of Majority Decisions. So it has all of my favorite topics right there in the title. And in particular, as we said last time, all this comparing voting functions is well and good for 2 candidate elections, but pretty much you should just choose majority. It's clearly the best choice. But what are you going to do if you have an election between 3 candidates? Then suddenly everything gets a lot harder if you know a little bit about social choice, you know that. So he was thinking about what are we going to do in France, maybe, if we have a three-candidate election, say A versus B versus C. What can we do? Well, again, you can imagine that you have, n voters. 1, 2, 3, etc. And each one of them has some opinion on A versus B versus C. And in fact, we're going to imagine that each one of them has a ranking of how they would rank A versus B versus C, let's say with no ties. OK, so maybe voter 1 thinks that like A is better than B is better than C. Let me get my example straight. 2 thinks that A is better than C is better than B. 3 thinks that B is better than C is better than A, and so forth. OK, so how are you going to aggregate these into like a societal outcome? All right, tough question. So Condorcet's suggestion was the following. Since we know and love two-party elections, let's just break A versus B versus C up into 3 two-way elections. So he was thinking, all right, let's just think A versus B, B versus C, and C versus A. So now everybody has an opinion on this. And when they're two-party elections, we like to call the parties plus and minus 1. So let me call A here plus 1, and B minus 1. And similarly, this is plus 1, this is minus 1, etc. OK, so what you can do is just translate everybody's three-way ranking into like 3 votes in the pairwise elections. So this person prefers A to B, and they prefer B to C, and they prefer A to C. And this person prefers A to B. Catch me if I get something wrong. B, C to B. And I'll just copy it. Minus 1, plus 1, plus 1. OK, and so forth. OK, so everybody translates their opinion into a triple of votes. And now you can just hold a pairwise election. OK, so in particular, let me try to draw this. If we call the A versus B votes the string x, and the B versus C votes the string y, and the C versus A votes the string z, these are length n Boolean strings, then you can just compute f of x given a 2-candidate voting rule. You can compute f of x, f of y, and f of z, and just take this as like societal, the societal outcome. OK? If you know the point of the story, don't spoil it just yet. So for example, Condorcet was like, all right, we also kind of know that the best two-way voting scheme is majority. Let's just try imagining using majority. So in this particular case, the majority would be plus 1 here. If there were also only 3 voters, plus 1 and minus 1. So that's equivalent to the ranking A greater than B greater than C. OK, so great. That's how you would hold the Condorcet election if F were majority of 3 with these particular votes. And let me also note, look at the columns in this picture. They're triples of bits, so a priori there's 8 possibilities, but there's only 6 rankings. So there's 2 columns that are never used. Which ones? Yeah, so in this picture you will never see, you'll only see the NAE, which stands for not all equals columns. OK, great. Now, somebody who's seen this before can tell me the trouble with this scheme. Yes, the outcome could potentially be all equals. I think there's an easy way to get that here with one flip of the switch. Maybe if I make this one up, if this happened to be plus, that corresponds to some other valid ranking. But then you'd have an outcome of plus, 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 which doesn't make sense. It's like society prefers A to B, and B to C, and also C to A. OK, so the Condorcet paradox is that the outcome could be one of these nonsensical triples, nonsensical, cyclic preference lists. And that's called irrational in the social choice literature. Okay, so Condorcet knew about this, and he's like, yeah, it's a problem. I guess he was like, well, what are you going to do? And it sort of stumped, in some sense, social choice studiers for a long time. Like, lots of people proposed different kind of ways of aggregating people's votes in a three-party or a more than three-party election. But there's always some kind of difficulties arising, just like this one. And the situation kind of came to a head like many, many years later, in 1950, with a gentleman called Arrow. He was a PhD student at Columbia. And he proved the following theorem. For which, as I said, partially he won the Nobel Prize. So Condorcet died in jail, and he got the Nobel Prize. Let F be any two-voter or two-party voting scheme whatsoever, and just assume that it's unanimous. I don't know if you remember this property. It just means that if everybody votes one way, then that's the outcome. So that's an extremely weak hypothesis, and a natural one. And suppose that in a three-way Condorcet election like this, F has the property that F is such that the outcome is always rational. So you never have the paradox using F. That would be great. And what Arrow says is, yeah, it's great, but there's only one way to achieve that, which is a horrible way. F must be a dictator. Okay, so actually, there is a two-party election scheme you can use in the Condorcet framework such that you will never get an irrational outcome. Just use the dictator scheme. If it's the third person's vote, he's going to vote or she's going to vote in a rational manner, so the outcome will be rational. But as soon as you try anything else, you will get some chance of having one of these paradoxical outcomes. Actually, this is very slightly weaker than what Arrow's theorem proved. Strictly speaking, Arrow proved this if you're allowed to use three functions, f, g, and h here. There's actually an easy reduction to the one function case. So this is really Arrow's theorem. OK, so there's various proofs of it, all of which are like kind of combinatorial, most of which are combinatorial and take like 1 page to 10 pages. I guess 1 page is better. It's not that hard. But Gil-Kalai gave a new proof, which I like very much, in 2002. And it's better in that it gives a sort of a robust version of the theorem, as we'll see at the end of the class. And he did it by really focusing on the question of what's the probability of a rational outcome under this impartial culture assumption. Here, impartial culture means that all the voters are independent, and they vote uniformly at random from their 6 choices here. So he said, fix f. Let's look at this quantity, the probability of a rational outcome, when you use f in a three-way Condorcet election. And you see, Arrow's theorem, you can phrase this hypothesis exactly as the hypothesis that the probability of a rational outcome is 1. Okay? I mean, if f is always rational and the probability is 1, if there's some way, some outcome of the votes where f leads to an irrational outcome, then the probability of getting an irrational outcome will be like strictly positive. So these two things are equivalent. OK, so this is what Kalai did. And if you look at this probability, something very nice happens. It's exactly equal to 3/4 minus 3/4 times the noise stability of f at parameter rho equals negative 1/3. Okay, that looks a little crazy, but that's a fact. And we'll prove that in like one board or two boards in a second. It's a simple calculation. But let's take this little lemma as a fact for now and see how we can deduce Arrow's theorem. Okay, so Arrow's theorem says it's a hypothesis. Let f be a function. Let's even forget for a second about this unanimous thing. It's a very minor hypothesis. So let's just say f is some function. And suppose we know that when you do a random election, the probability of getting a rational outcome under f is 1. Let's try to prove that that means f must be a dictator. You can see it's almost kind of looking similar to that calculation we did showing that the quantity that the function which maximizes noise stability among unbiased functions is a dictator. Okay, so this little lemma that Kalai proved, let's start with it. The probability of a rational outcome is this. And let's just write out the Fourier formula for this. So that's equal to 3/4 minus 3/4. And then noise stability, it's no longer up here, but you take the weight at level 0 plus rho, which in this case is minus 1/3, the weight at level 1, plus rho squared, the weight at level 2, plus rho cubed, the weight at level 3, etc. Okay? Remember these weights, they're sum of squares of Fourier coefficients. They're all non-negative. Now let's look at these coefficients that we have. Namely 1. Let me stick in a 1 here. 1, minus 1/3, a 9th, minus 1/27. If you plot them, they're going like this, right? They get like that. In particular, the smallest coefficient that's going to be up here is what? I didn't say smallest in absolute value. I mean literally the smallest, closest to minus infinity. Yeah, should have specified. The least value here is minus 1/3. So that means this is at most what you would get if you just had, because you have a minus here, so I'm putting at most. What you would get, this would be most negative if you just took all minus 1/3. So I'll factor out this minus 1/3 and get W0 plus W1 plus W2, sum of all the weights. Okay, this is just the sum of all the Fourier weights of f. So this is equal to 1 by Parseval. Okay, so then we have 3/4 minus 3/4 times minus 1/3, which equals 1. So far, it looks horrible. We've managed to show that the probability of a rational outcome is at most 1. Terrible, but this was actually a smart thing to do, because we can look at when do we have equality here. Yeah. This is the only inequality in the whole picture, and we have equality here, again, if all of the Fourier weight is concentrated on the guy with a minus 1/3 coefficient. So it's with equality if and only if all of the Fourier weight is at degree 1. Okay, so it's if and only if f is homogeneous and linear, and as we saw in the homework, that's equivalent to f being plus or minus a dictator. So we basically proved Arrow's theorem. I mean, we've shown that for getting the unanimous thing, if f is such that the outcome is always rational, we have equality, then f has to be plus or minus a dictator. Okay, and then if f is rational, then it would have to be the plus dictator. Sorry, if f is unanimous. Unanimous. Okay. Well, that's great. We proved Arrow's theorem in a snap. Oh, we still got to do this lemma. But actually, what I want to add is that it's actually, we proved something better than Arrow's theorem. I don't quite have time to expand on this, but you could also ask, OK, we saw that it's equality if and only if all the weight is at level 1. But you can also roughly easily see that it's approximate equality. I mean, it's nearly 1, if and only if the weight at level 1 is approximately 1. What I'm saying is if you want to get really, really close to 1, you better put almost all your weight here. Because all of these numbers, these other coefficients, are not just bigger than minus 1/3, but they're bigger by a significant amount. I mean, the second biggest one is minus 1/27. Yeah?
If we take out the unanimous requirement,
Yep.
isn't a constant function also always rational?
No. It's actually always irrational.
I see.
Yep. It has all its weight at level 0. So you get 3/4 minus 3/4 times 1, which is 0. So actually, that checks out. Yeah, so here, the fact that constants somehow get ruled out because this row parameter is negative. Yeah, so just as this aside, Kalai makes Arrow's theorem kind of robust. You can prove that you have almost equality if and only if f has almost all its weight at level 1. And you might ask, is it true that, let's say, if the weight at, is this the same as almost being a plus or minus dictator? You might ask, if the weight at level 1 is some 1 minus delta, is f close to being a dictator? We know if all the weight is at level 1, it has to be a dictator. Is there some function that's totally unlike a dictator that has like 99.9% of its weight at level 1? That's not an especially easy question to answer. But it's true. This is a theorem called FKN theorem due to Friedgut, Kalai, and Naor from early 2000s. It takes a little bit of work. We'll eventually prove it. But it gives you like the robust version of Arrow's theorem, that you can only sort of almost always be rational if you're almost always the same as a dictator. OK, so I have 5 minutes left, which is just enough time to prove this lemma, and then we'll be done. Any more questions? No? OK, so let's prove that formula. OK, so remember the situation here. We're choosing x, 3 strings, x, y, and z. These are the sort of the binary votes in the 3 two-way elections. And how are they chosen? Each of the n voters, if you look at like a column, chooses a ranking, one of the 6 rankings at random. And in particular, each column is one of these not all equal columns. And what we're interested in is the probability that the outcome, f of x, f of y, f of z, is also not all equal. That's when we have a rational outcome. So what we can do is write the indicator random variable for the event that these guys are not all equal. And we can, in fact, even do that using Fourier analysis. So let NAE be the function that takes 3 plus or minus 1 bits and outputs either 0 or 1, which is the indicator of not all equal. OK. So I could have, on your homework, asked you, please tell me the Fourier expansion of this function. And you would have then told me this. It's on the bits w1, w2, w3, it's equal to 3/4 minus 1/4 w1, w2, minus 1/4 w2, w3, minus 1/4 w1, w3. So it's degree 2. It actually has no degree 1 part. In fact, it's an even function, if you remember what even means. Oh, that's not quite. Well, anyway. And you can just check it for yourself now. Like, if all three of these guys are 1, then you get 3/4 minus a quarter, a quarter, a quarter. That's 0. If 2 of them are 1 and one of them is -1, then 2 of these products will be -1. You'll get 3/4 plus a quarter minus a quarter. OK, take my word for it. That's the formula. So therefore, the probability of a rational outcome is the expectation over x, y, and z chosen in this way of this thing, 3/4 applied to f of x, f of y, f of z. This is the formula we're shooting for. OK. And what I want to claim to you is this. Well, obviously, we can write this as 3/4 minus a quarter, the expectation of f of x, f of y, minus a quarter, the expectation f of y, f of z, minus a quarter, the expectation of f of x, f of z. And I claim that x and y are a -1/3 correlated pair. If you just look at x and y. Now, if you believe that, then you see this expression, the expectation of f of x, f of y, when x and y are -1/3 correlated, is just the stability at -1/3 of f. And everything's symmetric. Y and z are also -1/3 correlated, and same with x and z. So you'll get 3/4, and then 3 times you'll get the noise stability at -1/3 of f, which is what we're shooting for. OK, so the last claim is just to check this. The last part of the proof is just to check this. OK, and now let's just think about it. Each of the pairs xi, yi are independent, just like they should be in row correlated pairs. That's just because we're imagining the voters are voting randomly. What's the probability that xi equals, let's say, 1? Well, it's a half, because if the voters are voting randomly, a voter is equally likely to prefer A to B and B to A. And similarly, they're not independent, but the probability that yi equals 1 is also a half, because a voter is equally likely to prefer B to C than C to B. So to check this, it just remains to compute what's the probability that xi equals yi. Well, xi can equal y in just 2 ways. You can have plus, 1, plus 1, but then you have to have -1 here. Or you could have -1, -1, but then you'd have to have plus 1 here. So there are 2 ways they can be equal out of the 6 possible ways. So that's 1/3. So therefore, the expected value of xi, yi is 1/3 minus the probability they're unequal, 2/3, which is -1/3. OK, this is just a little calculation. OK, that's the end of the proof. Question?
Could we have used this method to prove the theorem for 3 functions?
Oh, in the Arrow version of Arrow, where instead of all the elections are held with f, like the first one's held with f, one is held with g, one is held for h? No, it's not so easy. Because you'll get some kind of like cross noise stability between f and g and h and f here. And that's not easy to analyze. So the answer is no. There may now be, I'm not sure, but it's not easy. There's only the non-robust version, because there's a simple reduction in Arrow's theorem that if the probability of a rational outcome using f, g, and h is all 1, is equal to 1, you can never have an irrational outcome. That's a pretty strong condition, and you can use it easily to combinatorially prove that f must equal g must equal h. And then you can do this proof. Good question, though. Any more questions? OK. Oh, yep.
We stated, I think we stated Arrow's theorem for like, oh, so was this was Arrow's theorem for just 3?
Yeah, that's also kind of a cheat. This Arrow's theorem for 3 candidates. But Arrow's theorem for like more candidates does follow from 3 candidates, because if you have more, you can kind of ignore the ones that are in excess of 3. It's not quite as simple as that, but the version for more than 3 candidates follows from the... Yeah, Arrow's theorem has this hypothesis called independence of irrelevant alternatives, which is the same as the assumption that you're doing a Condorcet election, except that you have to also allow different functions f. OK, thanks. See you next time.